Good afternoon, everyone. Happy to be kicking off the IP Optical session. So again, I'm Rafael Francis, and what I'd like to talk to you about is what comes next. So now that we've successfully deployed the first phase of these converged IP optical networks, where do we go from here? How do we scale these deployments? How do we achieve better IP optical integration? What I'm referring to here is harmony. But before we get into that, let's look at where things stand today. So this is a survey conducted by Heavy Reading where they were asking service providers about their adoption of routers that support coherent optics. And as you can see here from, if you combine the two numbers in white, effectively service providers said 95% of them said they're deploying or plan to deploy coherent routers, and 58% of them saying they're deploying them extensively, with only 5% saying they're going to stick with traditional routers that don't support coherent optics. So coherent router adoption's accelerating. We see that. And we also see that coherent pluggable adoption is accelerating. So this market data is for pluggables sold into service providers. Of course, hyperscalers we know are deploying coherent pluggables to a large degree. In this case, you can see with service providers, it's ZR Plus optics that are driving a lot of that growth. But in all, you can see it's 52% annual growth rate of all these different coherent optic variants within service provider networks. So again, the point being, as coherent routing grows, how do we evolve these solutions? How can we keep pace with that growth? And so what I'd like to talk to you about is three ways in which we see that these solutions need to evolve. So of course, first of all, you're going to have faster routers, faster optics, 800 gig and beyond. You're going to have tighter integration between the IP and optical layers. That's going to come through better multi-layer software. And then finally, you're going to have architectures that give you more of a freedom of choice, more flexibility to accommodate that traffic growth, okay? So first, let's start with the fact that if you look over the last 10 years, router silicon has doubled roughly every 2 years, to the point where now we have 800 gig capable routers with 100 gig SerDes coming from the ASIC. Similarly, if you look in parallel, coherent optics has doubled roughly every 4 years from CFP to CFP2 to QSFP-DD, and now QSFP-D 800, right? Which aligns nicely with the 100 gig SerDes because you need 8 of those to drive that 800 gig coherent optic, okay? So routers are getting faster. 800 gig pluggables are here. So 400 gig is where the volume is today, but with the introduction of 800 gig, we're going to see more use cases addressed, greater reach. We're also going to see variants of 800 gig coherent that are aligned more with IEEE Ethernet standards, addressing some shorter reach use cases, campus, if you will, with technologies like 800LR that brings other advantages such as lower latency, for example. We'll also see in the future 1.6 terabit pluggables, but these are a bit further out. These will necessitate 200 gig SerDes on router ASICs, which we're expecting around the 2026 timeframe. And then of course there'll be, beyond that, there'll be other applications for coherent plugs, shorter reach applications such as in data centers, but really this is kind of beyond the scope of today's talk, okay? So we see there's lots of different plug options, right? And plugs will get you far, but they won't get you everywhere. So one of the things that we do at Ciena is we analyze, we do a lot of analysis of coherent optics and see where they make the most sense. And in this case, this is an analysis that's comparing different coherent optic types, such as 400 gig pluggables and routers, 800 gig pluggables and routers, and a 1.6 terabit embedded optic, such as what we support in our Wave Router platform. And it's comparing the cost effectiveness of these different technologies across different real-world network routes, a short route, a medium route, and a long route. And here we use 400 gig as the baseline, right? And we've normalized the cost, right? So we're not sharing cost data. And what you can see is pluggables outperform, they're the lowest cost solution for shorter and medium routes. In fact, 800 gig pluggables outperform their 400 gig predecessors, where 800 gig plugs are 88% of the cost per gig compared to 400 gig for short routes, and 81% of the cost per gig for medium routes, so on and so forth. But what you can also see is that for the long routes, actually an embedded optic is more cost effective. And that's because if you look at the longer routes, the photonics portion of the cost becomes a larger proportion of the cost, and the spectral efficiency and the reach of a high-performance embedded optic, results in a lower cost per gig, a lower cost of ownership. Now that was, let me jump back, that was with fiber costs excluded. If I now bring in the cost of the fiber, right, and amortize that cost, and this is just looking at full fill on a pair of fiber, right? If I look at the cost of that fiber, the advantage of the embedded optics becomes even more apparent, right? Where the embedded optics kind of approach parity cost per gig with the 800 gig pluggable in this case. But again, if you look at the long route, 56% of the cost per gig when compared to the 400 gig plug. Now, that's looking at cost. What if we use another metric? What if we look at the amount of capacity that you can drive over a pair of fiber, right? And so here we're looking at capacity in terms of how many 400 gig services can I accommodate on that pair of fiber. And what we see here is that the embedded optic actually supports anywhere from 1.3 times the capacity up to double the capacity on a pair of fiber for the longest routes. Okay, so the point here is that this is not a one-size-fits-all, and if you have an architecture such as a modular router that can support a mix of coherent pluggables and embedded optics, you can cover all of these technical and economic use cases, right? So that's the first way in which solutions are evolving. The next way in which they're evolving is through better software. And I take zero credit for that animation because I have no idea how to do that in PowerPoint. But this is really, this is something that at Ciena we've invested a great deal in, and that is looking at better multi-layer software across all the different phases of a life cycle of an IP optical network, from planning to provisioning to troubleshooting to optimizing that network. Now, today we won't have time to get into all of these. I'll share with you some of the things that we're doing on the design and planning side of things. A colleague of mine, Robert Friskney, is going to be talking about provisioning and then troubleshooting with multi-layer visualization later on this afternoon. But if I take a moment to talk about each of these other ones in black, so multi-layer software for better resiliency is about if I'm aware of the relationship between the IP and the optical layers, I can do things like propagate SRLG information from the optical layer to a controller and then back down to the router, so that when I'm implementing even IP protection schemes like TI-LFA with segment routing, I can do so in such a way where I don't end up with a single point of failure in my optical network. Optimization is about doing things like looking at available capacity in the optical layer and mining that available margin or capacity to deliver it to the IP layer for more overall utilization, better utilization of the network. And then management or multi-layer coordination is about doing things such as, let's say you have to perform maintenance on a photonic line system. Automatically having the IP layer divert traffic off of that link so that I can perform that maintenance and automatically revert it back in a way that I don't have a bunch of manual steps involved in doing it the way it's done often today. So let me get into the design and planning piece. And first I'd like to share with you a challenge that one of our, a tier 1 operator in Europe basically cited, which is that whenever we need additional capacity between links, some of the things that we have to do is figure out, what's the modulation we need to use, what's the optimal, let's say, pluggable optic to use. And the way that we used to do that is the optic vendor would help us make that determination. When I now take this coherent WDM technology and I put it into a router, now I have to perform those calculations myself. So that is, unless we give them the software tools to do it. So that's what I want to show, some of the improvements that are being made in multi-layer software to facilitate this. So this, for example, you can take real fiber route data, fiber characteristics, and you can feed it into a planning tool, right? Even things like IP traffic demands, to feed it into a planning tool. And you end up with, effectively, think of it as like a digital twin, where basically you have a real-world network here, which is a pan-European network, an actual network, right? And this network has 60 routes, okay, and there's varying distance of these routes up to 2,700 kilometers. And what the design and planning tool allows you to do is to figure out what is the optimal technology to deliver the traffic demands on each of those routes. Do I use a 400 gig plug? Do I use an 800 gig plug? Do I use an embedded optic? And you can actually have multiple variants of these. I could have different transmission modes modeled within this. I can have different gigabaud rates modeled within this. And it'll tell you what the optimal choice is. You can even drill down into a particular route and you'll get a scorecard that compares and why did it pick this particular technology, 800 gig pluggable in this case, based on comparing capacity, cost per gig, power, space utilization. And in fact, you can even tailor the criteria to your needs. So is it more important for you to achieve lower cost? Is it more important for you to achieve, to reduce your power? All of that can be tailored to meet your needs. So what we hear from planners is this is something that used to take days, if not a week or more, to figure out the optimal solution here. This brings it down to an hour. So huge gains in operational efficiencies. The last way in which these IP optical or coherent routing solutions are evolving is in the flexibility of the architecture. So how do you optimize the architecture as traffic demands grow? So let's take this physical topology consisting of a hop-by-hop routed network and start to overlay traffic onto it and fill up that network where we grow the capacity to 9 times. But let's compare that hop-by-hop architecture with an architecture that uses selective or targeted optical express links between certain routers to bypass when you have all this traffic growth. And what we see is that deploying a photonic layer via ROADM helps to significantly reduce the amount of deployed capacity you have to deploy, or what we're calling here the transit tax, as those traffic demands grow. So the key takeaway here is deploying that separate photonic layer, gives you that flexibility as your traffic demands grow and allows you to keep your costs in control. But, don't take our word for it. This is actually a real-world example of BT, who published a study wherein they took their entire nationwide UK network and they were looking to determine the value that ZR Plus optics could deliver within their scenarios. And they were looking at different architecture alternatives, such as hop-by-hop, such as optical expressing. And you can see what they found is that optical express is cheaper than the hop-by-hop approach, as traffic grows, and you can see the crossover point there between the red line and the yellow line. Furthermore, putting a ZR coherent plug in a router as opposed to putting that ZR coherent plug into a separate transponder further reduces cost, further reduces things like space and power. And then finally, what I would say is that an optimal solution could really be a combination of all these, right? So when traffic is lower or you have fewer hops, then you may use a hop-by-hop approach. When traffic is growing, then you may need to use more of these optical express. Now, I'll point out that this study did not include embedded optics in its comparison. It was just looking at pluggable optics. And I'll also point out that if you're still looking for scenario A on the chart, it's not not there in this chart. Scenario A was actually it was higher cost than scenario B. It was hop by hop without any sort of transmission or amplification. But if you're looking for the full study, I've given a source there at the bottom. Feel free to reference it. And I want to thank Russell Davey from BT and the publisher Optica for allowing us to reference this study. So with that, I'll just wrap up by saying, as these IP optical networks grow, solutions have to evolve. You need faster routers, faster optics. That's a given. You're going to need better multi-layer software and then flexible architectures, right? So if you'd like to discuss this further, please feel free to come find me or visit us at our booth. Thank you.